Hey friends, welcome to the YouTube channel all about electronics. So in the last video we had seen that what is transient analysis and what is the importance of this transient analysis. And then after we had seen the behavior of the basic components during these transients. So in this video we will see the transient analysis for the first order RC and the RL circuits. So in this video we will see the transient analysis for the first order RC circuit and the first order RL circuits. And for these circuits we will see the two kind of responses. The first is the source free response and second is the force response. So the source free response is the response of the circuit when there is a no source connected into the circuit. While this force response is the response of the circuit when there is some kind of force input excitation is given to the circuit. So in this video we will provide a force DC excitation to this RL and RC circuits. And we will see how the circuit behaves for this force excitation. So let us start with the source free response for the RC circuits. So in this circuit the switch is at position number 1 since a long time, and at time t is equal to 0 this switch has been moved from position number 1 to the position number 2. So if we see the equivalent circuit at time t is equal to 0 plus, which is the just after the switch has been moved from this position number 1 to the position number 2, then the equivalent circuit will look like this. Now let us say the voltage across this capacitor is Vc. Now before this time t is equal to 0, let's say time t is equal to 0 minus. Since this voltage V is applied continuously across this capacitor, so the voltage across this capacitor will be V volt. Now at time t is equal to 0 plus, this switch will be at position number 2. And we know that the capacitor opposes the instantaneous change of voltage. So at time t is equal to 0 plus also, the voltage across capacitor will remain V. So this will be our initial condition. So now intuitively if you see, the charge across this capacitor will get discharged through this resistor. So initially the voltage across capacitor will be V volt. And with time this voltage get reduced, and at time t is equal to infinity or after a sufficient time, the voltage across this capacitor will goes to the 0. Now we don't know how this voltage is getting reduced. The voltage can go from voltage V to the 0 either linearly or exponentially or any other way. So let's find out how this capacitor is getting discharged through this resistor. So for that, let's apply a Kirchhoff's voltage law in this circuit. So applying KVL, we can write VR plus VC is equal to 0, where VC is the voltage across this capacitor and VR is the voltage across this resistor. That means IR plus VC is equal to 0, where I is the current that is flowing through this circuit. Now the same current I will also flow through this capacitor, and we know that the capacitor current can be given as C into dVc by dt. So we can write R into C dVc by dt plus Vc is equal to 0. So if we further simplify it, then we can write dVc by dt plus 1 over RC into Vc is equal to 0. So if you see this equation, this is the first order linear differential equation, and there is a no force excitation in this equation. That means this Q is 0. And as this Q term is 0, so the solution of this equation will only contain the source free response or a complementary function only, and Pi term, that is a particular integral, will be 0. So the complementary function or a source free response for the first order linear differential equation can be given as A into e to the power minus pt. So similarly for this equation we can write the solution Vc as A into e to the power minus t over Rc. So now to find this coefficient A, let's apply a initial conditions inside this equation. So at time t is equal to 0 plus, we can write this equation as A into e to the power minus 0. That means Vc is equal to A. So now we know that at time t is equal to 0 plus, the voltage across this capacitor will be V volt. So we can say that the value of A will be V volt. and if you put this value inside this equation, then we will get Vc of t is equal to V into e to the power minus t over Rc. So this is how the capacitor will get discharged through this resistor R. So now here this Rc is known as the time constant of the circuit, and we can denote this Rc as capital T. So now we can represent this equation graphically as follows. So at time t is equal to 0, the voltage across the capacitor will be V volt. So now in this equation, if we put the value of t is equal to 1 Rc or a 1 time constant, then the capacitor voltage we will get as a 0.37 volt. So in 1 time constant, the value of a capacitor voltage will be only 37% of the original value. Similarly, in this equation, if we put the value of t as 2t, 3t, 4t and 5t, then you will get a corresponding voltages across the capacitor. And as you can see here, after a 5 time constant, the capacitor will get almost fully discharged. So we can say that capacitor will get fully discharged approximately in a 5 time constant. So suppose in your circuit, if you want that your capacitor should get discharged in some particular time, then by choosing the value of R and C, you can decide this discharging time. Let us say in your circuit, you want that your capacitor should get discharged in a 5 microsecond. Now we know that the capacitor will get discharged in a 5 Rc time constant. So this Rc time constant will be 1 microsecond. Now suppose if you have chosen value of R as 1 kilo ohm, then value of C will be 1 microsecond over 1 kilo ohm. So value of C will come out as a 10 to the power minus 9 nanofarad. So in this way you can choose your value of R and C to get a desired discharging time. So similarly, let us see now a source free response for the RL circuit. So in this circuit, the switch is at position number 1 since a long time, and the current I is flowing through this RL circuit. And at time t is equal to 0, the switch has been moved from this position number 1 to the position number 2. So at time t is equal to 0 plus, the equivalent circuit will look like this. Now at time t is equal to 0 minus, let us say the current that is flowing through this inductor is IL, and this IL can be given as I. That means the current that is flowing through this inductor will be I. Now we know that the inductor opposes the instantaneous change of current. So at time t is equal to 0 plus also, the value of this inductor current will be I. So now let us find out how this inductor current will change over a period of time during this transient. So for that, let's apply a Kirchhoff's voltage law inside this circuit. Let us assume that the current I is flowing inside this circuit, and VR is the voltage across this resistor and VL is the voltage across this inductor. So applying KVL, we can write VR plus VL is equal to 0. Now this VR can be given as I into R plus VL can be given as L into di by dt. So if we further simplify it, then we can write it as a di by dt plus R by L into I, that is equal to 0. Now if you compare this equation with di by dt plus pi is equal to q, then you can see here that q term is 0. So the response of the circuit will be only source free response, as there is no force excitation into this circuit. And response of the circuit can be given as A into e to the power minus R by L into t. So now to find the value of this coefficient A, let's apply a initial conditions. So as we have already found out earlier, at time t is equal to 0, the current that is flowing through this inductor will be I. So we can say that I of 0 plus is equal to A into e to the power minus 0. So we can say that I of 0 plus, that is equal to A, and value of this current I at time t is equal to 0 plus is I ampere. So value of A will be I. So if you put this value of A inside that equation, then we will get I of t is equal to I into e to the power minus R by L into t, which is the equation for the inductor current. And graphically, if you see this inductor current, the plot for this inductor current will be similar to the discharging curve for the capacitor. So at time t is equal to 0, the value of this inductor current will be I. and as the time progresses, the value of this inductor current will reduce, and at time t is equal to infinity or in steady state condition, the value of this current I will be 0. Now here the ratio of L by R is known as the time constant, and it can be denoted as a T. So we can write this equation as I into e to the power minus T by capital T, where T is nothing but a L by R. So now suppose if you want to find the value of a inductor voltage, then this inductor voltage VL can be given as L into di by dt. So now if you put the value of inductor current IL inside this equation and solve it, then we will get value of inductor voltage VL as minus IR into e to the power minus R by L into T. So in this way you can find the inductor voltage as well. So for this inductor voltage at time t is equal to 0, the value of inductor voltage will be minus IR, and as the time progresses, this inductor voltage gets exponentially decreased, and at time t is equal to infinity, the inductor voltage goes to the 0. So far we have seen the source free response for the RC and the RL circuits. So now let's see forced response for this RC and RL circuits. So we will provide some DC excitation to this RC and RL circuit, and we will see that how this circuit behaves during this transients. So let us say in this circuit at time t is equal to 0, the switch is getting closed, and this voltage V is getting applied across this capacitor. Now before this time t is equal to 0, here we assume that there is no charge across this capacitor, and at time t is equal to 0, once the switch is getting closed, the equivalent circuit will look like this. So at time t is equal to 0 minus, since there is no charge across this capacitor, so the value of a capacitor voltage Vc will be 0. Now we know that the capacitor opposes the instantaneous change of voltage. So at time t is equal to 0 plus also, the capacitor voltage will be 0 as well. So intuitively if you see, as this voltage V is applied across this RC circuit, the capacitor will start charging. So at time t is equal to 0, there will not be any charge across this capacitor, and as the time progresses, capacitor will start charging, and it will charge up to the voltage V. So now let's find out how this capacitor is getting charged up to this voltage V. It could be either linear, or it could be exponential, or it could be of any other form. So let's find out how this capacitor is getting charged through this voltage V. So for that, let's apply a Kirchhoff's voltage law inside this circuit. So applying KVL, we can write V is equal to Ri plus Vc, where Vc is the voltage across this capacitor. Now the same current I is also flowing through this capacitor. So we can write this current I as a capacitor current, and capacitor current can be given as C into dVc by dt. So we will get V is equal to RC dVc by dt plus Vc, and if we further simplify this equation, then we will get dVc by dt plus 1 over RC into Vc, that is equal to V over RC. So now if you compare this equation with di by dt plus Pi is equal to Q, then here P is nothing but 1 over RC and Q is V over RC. So now if you see here, we also have this force excitation inside this circuit. So now the solution of this equation will contain two terms, the particular integral and the complementary function. So the complementary function part will remain same as we have found earlier, which will be the source free response for the circuit, and the particular integral is the solution of the equation at time t is equal to infinity. So we can say that for the given circuit, particular integral will be nothing but a voltage across this capacitor Vc at time t is equal to infinity. So let us first of all find this particular integral, that is a Vc at time t is equal to infinity. So now we know that at time t is equal to infinity or in a steady state condition, this capacitor acts as a open circuit. So the value of Vc or a capacitor voltage at time t is equal to infinity will be nothing but a value V. So our particular integral will be nothing but a V volt. So now let us find the complementary function. So the complementary function or a source free response can be given as A into e to the power minus Pt form. and here the value of P is nothing but 1 over RC. So the source free response for the given equation will be A into e to the power minus 1 over RC into T. So the overall response for the capacitor voltage can be given as V plus A into e to the power minus T over RC. So now let's find out this coefficient A, and to find this coefficient A, let's apply a initial conditions. So at time t is equal to 0 plus, the capacitor voltage can be given as V plus A into e to the power minus 0. That is nothing but Vc 0 plus is equal to V plus A. And at time t is equal to 0 plus, as there is a no charge across the capacitor, so value of Vc will be 0. So we'll get V plus A is equal to 0, or in another term we can say that A is equal to nothing but minus V. So the overall response VCT can be given as V minus V into e to the power minus T over RC. And if we see this equation graphically, then it will look like this. So at time t is equal to 0, there will not be any charge across the capacitor, and the value of capacitor voltage will be 0. And as the time progresses, the capacitor will charge exponentially and it will reach maximum value up to the voltage V at time t is equal to infinity or in a steady state condition. So in this equation, first of all, let's put the value of t as a 1 RC or a one time constant. So we will get value of capacitor voltage as a 0.63 volt. So we can say that in a one time constant, capacitor used to get charge up to the 63% of its final value. And similarly, if we put value of t as 2 time constant, 3 time constant, 4 time constant and 5 time constant, then you will see that capacitor will reach to its final value or approximately to its final value in a 5 time constant. So in your design, suppose if you want to charge your capacitor very fast, then by choosing the value of R and C, you can decide the charging time for the capacitor. So this is all about the force excitation for the RC circuit. So now let us see the force response for the RL circuit. So in this circuit, we are providing a DC excitation to this RL circuit at time t is equal to 0. So before this time t is equal to 0, we are assuming that there is a no energy inside this inductor. And as soon as at time t is equal to 0, the switch is getting closed, then this voltage will get applied across this inductor and current will start flowing through this circuit. So at time t is equal to 0 plus, the equivalent circuit will look like this. Now we know that at time t is equal to 0 minus, there will not be any current flowing through this inductor. Let us say IL is the current that is flowing through this inductor. So this IL can be given as 0 ampere, as there is a no connection with this voltage source. And we know that the inductor opposes the instantaneous change of current. So at time t is equal to 0 plus also, the value of this inductor current will be 0. So now for the force free response, let's find out this equation for the inductor current. So for that, let's apply a Kirchhoff's voltage law inside this circuit. So applying KVL, we can write V is equal to VR plus VL, where VL is the voltage across this inductor and VR is the voltage across this resistor. So we can write it as a IR plus L into DI by dt. So if we further simplify it, then we can write the DI by dt plus R by L into I, that is equal to V by L. So now if you compare this equation with di by dt plus pi is equal to q, then the value of p will be R by L and value of q will be V by L. So this V by L is the nothing but a force excitation for this given circuit. And as the circuit contains a force excitation as well, so the solution of the equation will be having a two terms, the particular integral and the complementary function. So this particular integral is nothing but the solution of the circuit at time t is equal to infinity, and this complementary function is the solution of the circuit or equation for the source free response. That means when there is a no source connected inside this circuit. So first of all, let's find out this particular integral. So this particular integral is nothing but the inductor current at time t is equal to infinity. So at time t is equal to infinity or in a steady state condition, this inductor will act as a short circuit. So the current that is flowing through this inductor IL can be given as V upon R. So the value of particular integral for our case will be nothing but a V over R. Now the complementary function or a source free response for the circuit can be given as A into e to the power minus pt, and here the value of P is nothing but R by L. So the solution or a complementary function solution for the circuit will be nothing but A into e to the power minus R by L into T. So now if we combine this particular integral and the complementary function, then the overall solution for the circuit will be nothing but V by R plus A into the e to the power minus R by L into T. So now to find the value of this coefficient A, let's apply an initial condition. So at time t is equal to 0 plus, we can write this equation as V by R plus A. And we know that at time t is equal to 0 plus, the value of inductor current is 0. So we will get V by R plus A, that is equal to 0, or we can say that A is nothing but minus V over R. So we will get inductor current IT as V by R minus V by R into e to the power minus R by L into T. And graphically if you see this equation, the plot will be similar to the charging for the RC circuit. So at time t is equal to 0, the inductor current IL will be 0. And as the time progresses, the inductor current will increase exponentially and it will reach maximum value up to V over R. So this is all about the force response for the RL circuit. That means the circuit has given some DC excitation at time t is equal to 0. So in this way we got equations for the capacitor voltage and the inductor current for the RC and RL circuits for the force excitation as well as the source free responses. So now let us see the shortcut method using which we can easily find these equations. Now using this shortcut method, the capacitor voltage or an inductor current can be given as final value plus initial minus final value into e to the power minus t by t. So let us take a case for this force excitation for the capacitor. So for the force excitation for the capacitor, final value or a voltage across the capacitor at time t is equal to infinity is nothing but a V. And we know that initially the voltage across the capacitor is nothing but 0, and at final value of the capacitor is nothing but minus V. So this initial value minus final value will come out as a minus V, and that will be get multiplied by the E into e to the power minus t over t. Now for this RC circuit, the value of t is nothing but RC. So overall equation will get as a V minus V into e to the power minus t over RC. This is the response of the RC circuit for the force excitation. Similarly, let's try to find out the source free response for the RC circuit. So we had seen that for the source free response, the final value or a value across the capacitor at time t is equal to infinity is nothing but a 0, while the initial value of a voltage across the capacitor is nothing but a V volt. Again the final value will be 0, and that will get multiplied by the equation E into e to the power minus t by t. So we will get source free response as a V into e to the power minus t by RC. So in this way, using this equation, you can easily find the value of either capacitor voltage or a inductor current in a very short time. So now so far whatever circuits that we have discussed, we have assumed that the circuit contains only a single resistor and a one reactive element, either inductor or a capacitor. But it might happen that your circuit may contain more than one resistors in the circuit. Let us take one example. So if you see this circuit, in this circuit we have total 3 resistors, this R1, R2 and R3. So in such scenarios, what we do, we used to find a equivalent resistance for the given circuit. So first of all, to find this equivalent resistance, draw the circuit time t is equal to 0 plus. So at time t is equal to 0 plus, this switch will get closed. So the equivalent circuit will look like this. Now in this equivalent circuit at time t is equal to 0 plus, find the equivalent Thevenin's resistance across this capacitor. So to find that, just remove this capacitor from the circuit and find the equivalent resistance across these two terminals. And we already know to find the Thevenin's equivalent resistance, we used to remove all the sources inside the circuit. So this voltage source will also get short circuited. And if you see now, this R1 will also get short circuited. So the equivalent resistance across these two terminals is nothing but the R2 in parallel with a R3. So this will be the equivalent resistance across this capacitor, and the time constant RC can be given as R equivalent into C, that is R2 parallel R3 into C. So in this way, when your circuit contains more than one resistive element, then you can find the equivalent Thevenin's resistance across this reactive element. So now let us see the summary or a procedure to find the transient equation for these RC and RL circuits. So first of all, draw the circuit at time t is equal to 0 plus. How the circuit looks like at time t is equal to 0 plus. The second step is find the initial conditions for the given circuit. That means what is the capacitor voltage at time t is equal to 0 plus if it is a RC circuit, and find the initial value of the inductor current if it is a RL circuit. Then after, if your circuit contains more than one resistive element, then find the equivalent resistance of the circuit. And your time constant T will be nothing but R equivalent into the C equivalent. And if your circuit is RL circuit, then your time constant T can be given as L equivalent divided by R equivalent. Then after, find the final values of this capacitor voltage or inductor current at time t is equal to infinity. And then after, find the particular integral and the complementary function for the given equation. Or you can use a shortcut method, that is a final value plus initial value minus final value into e to the power minus t by t. So using this, you can find the total solution for the given RC or a RL circuit. So I hope in this video you understood how to find the transient equation for the RC and RL circuit for the source free response as well as for the forced DC excitation. So in the next video, we will solve some problems for this first order RC and the RL circuits. If you have any question or suggestion, please let me know in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.